screen. I mean, I will introduce Chris, but I really shouldn't. He doesn't need introduction. He's a tenured associate professor of computer science at the University of Rochester and has secondary appointments, as per his website at least, in brain and cognitive sciences, the Georgian Institute for Data Science and the Center for Visual Science. I mean, he has like a broad impact in machine learning in general, continual learning, industry, even with startups and stuff. And so the title of the talk, I guess, is pretty much aligned with this: computational efficient continual learning for real-world applications. Chris, if you are good to go, the floor is yours.
Good. Thank you so much, Andrea. So, yeah, so here's going to be my argument today. For the most part, nobody cares about what we're doing here, except for us. We're writing papers for other continual learning people. And I think, and I've gotten a lot of anecdotal evidence for this, where I keep talking to people in industry and they say, yeah, I learned about what you guys do. I don't care. This doesn't help me. So, and I don't think it has to be this way. I don't want it to be this way anymore. So I think we can have enormous real-world impact, but we have to align our work to real-world use cases. So that's the thing that I think is really missing in the vast majority of the work going on right now. So I'll give you two examples. It's certainly not an exclusive list or anything like that, like open world learning could be another example. But two that I think there's big demand for are updating production AI systems and on-device learning. So in industry, oftentimes people are retraining giant neural networks periodically from scratch. So basically, you queue it up, you queue up your data, and you have a job that triggers like once a month to retrain. For continual learning to be useful, though, it must be more efficient than periodic retraining. So why retrain from scratch? We could just use continual learning if continual learning worked as well as the offline model and used less energy, used less compute, right? That'd be great. So, you know, we can even reduce greenhouse emissions. We can claim we're advancing green AI. Ready, we're saving the world. Probably not go that far. Okay, on-device continual learning. So this could enable personalization and is already being used in augmented reality systems. I had chats with a couple companies about this who are using it for things like this, but they don't seem to publish much. But what do we need from continual learning to do this? Well, we need a mobile-friendly architecture. If you're going to be using a giant vision transformer, it's a non-starter. You're going to need limited memory and storage, whereas in the industry example, they don't care. And you're going to need something like low-shot or semi-supervised learning, and you should be looking at that and monitoring that and measuring that, because for these on-device applications, you're not going to have hundreds and thousands of labeled samples. That's not going to happen. So you have to think about your use case. So if you look at these requirements here, I tried to make a little plot table. Must match offline model with production AI. That's going to be critical. Otherwise, I'm not going to sacrifice my accuracy. On-device AI, well, do your best. Must save money, yes. For the on-device, it's like, well, you want to do it, you've got to do it. Storage constraints, production AI people don't care. On-device, well, you've got some serious storage constraints. Must have sample efficiency for both if we're really going to be efficient. Learning must be computationally efficient for both. Low-shot learning on-device. Effective for arbitrary learning distributions, both of these. And oftentimes people test on just a single adversarial distribution and even design the algorithms for explicitly an adversarial distribution. And if you take their code and run it on any other distribution, it doesn't work. And I think nobody needs that. Nobody needs your class incremental learner. If that's all it can do, it's not useful. And it needs to work on real-world inputs. For these applications, nobody's going to trust your work if you only trust it on C/10. Mobile network architecture, yeah, on device, definitely not applicable to production AI. So my argument is most of our work really does not match these needs. We conflate tests of a continual learner's abilities as the goal rather than simply a test. Like this is really succumbing to Goodhart's law, right? When a measure becomes a target, it ceases to be a good measure. So like we were among the first people to like propose classic incremental learning as a great test for continual learning in terms of, hey, here's a really adversarial distribution to test on. Then a bunch of people designed algorithms that only work for that scenario. It's like, nobody needs that. It was a test. So to be a useful robustness, it is useful as a robustness test, right? But when in the real world are you going to have only data from new classes arriving? That'd be very unusual, and I don't think you can necessarily expect that. C for 10, C for 100, or even like mini ImageNet and things like that. If you can't scale to high resolution images or whatever your modality is in a large number of classes, it's probably not very useful. We've been using ImageNet here for over 6 years, so I really don't understand the arguments when people say it's too expensive, especially since I'm going to argue that computational efficiency should be what we focus on. And if you look at how much does it cost today to train, so here's this guy, Jonathan Frankel, he's been going around giving talks about this recently, saying, if you only test on C10, you'll reject a NeurIPS paper. But didn't work in continual learning, it's $10. So it's $10, and that's if you don't own the hardware, right? That's if you scrub. That's not that much. And we've been doing that on GPUs that are 7 years old, but we don't pay for electricity, the university does. We've got to buy hardware. Storage, like I said, I don't think that matters for industry. So as Amaya had been chatting about, takes about 6 cents to storage net. They don't care about storage costs. Like, it's usually not a big factor unless you're in like an extreme regime. Compute dominates all of these expenditures. And if we can make continual learning more efficient and retain the performance of the offline model, they would love that. So if you do want to focus on the storage constraints, though, then probably your whole paper should be thinking about on-device learning. And that's how you should angle it. And you should then measure things like low-shot learning. Think about semi-supervised learning, because if that's going to be your pitch, then where you're in a storage constraint space, then you're thinking about, on-device learning. So unfortunately, if you start measuring the amount of compute used by our continual learning algorithms, it's not good. Here's the offline model here. Here's some popular ones that use ImageNet, and they're more expensive. This is a number of updates than the offline model. This isn't good. This is not that helpful, right? These are more expensive than training the offline model, and they work worse. So there's no benefits. So that's a problem. So I'm going to talk about 3 projects that try to move us towards efficient continual learning. I don't have a lot of time, so I'm just going to give you the highlights. We use a lot of data sets for this, but I'll focus on the ImageNet results. And all of them do test classic incremental learning, as an extreme adversarial example of a distribution. But we also test IID orderings. Why? Well, it's a super easy distribution. So, if we work well for both, at the very least, we know our code works for arbitrary distributions. I mean, there's tons of other ones we try. So anyways, here's Siesta. It's joint work with my student, Yusuf Haroon, Jair Gallardo, and Tyler Hayes, who is graduated, and Ron Kemper, who graduated a long time ago. Anyways, so Siesta, it's kind of like, if you're familiar with our Remind model, it's kind of like Remind on steroids. Like, it's very similar, but we kind of changed a handful of things and changed how it's trained. So, but basically the idea is it's inspired by something called hippocampal indexing theory, and uses latent rehearsal or latent replay, if you will, where it kind of compresses stuff from that. It compresses stored tensors and reactivates them in order to update the top layers of the network. The frozen layers just consist of 2% of the network, so very little of the network is frozen, and 98% of the network is plastic and can change. Basically, it goes through 2 phases. In a wait phase, it stores compressed experiences and updates its output layer only. And during its sleep phase, it uses our latent rehearsal here with a compute budget, where some compressed experiences, not all of them, are reconstructed for rehearsals. We got a budget. Okay, here's just one plot about this whole pre-sleep, post-sleep thing. Sleep helps you too. There's lots of studies showing sleep helps your learning. You get better at things. And then here's just the I'll get to the compute here in a moment, but here's, Remind versus Siesta, since I mentioned it's kind of like an upgraded version. It's better across the board, across data sets. But it trains 4.3 times faster on ImageNet and 4.4 times faster on this place's standard data set. And look, 0 forgetting. There's the offline model. Boom, problem solved, mostly. So that's good, right? It's gets 0 forgetting under these conditions. It works for arbitrary distributions. So, we even using hypothesis testing, we found no significant difference between these 3 scenarios. It's very much more efficient than existing methods. You can kind of see here the number of updates required to reach a certain level of performance versus other methods requiring far more updates. And also some of them use gigantic model, like look at the parameters here, like very big. Ours are kind of like we're using mobile networks, so they're pretty tiny. But yeah, I should say it takes about 2 hours to train all of ImageNet with this. So pretty cheap, and it's pretty cheap. Here's just all the models versus it. Just take the numbers out of the papers. These experiments are here kept fair, like everything is equal, like same models, same backbones, everything else. This is more they just compare all the models. Okay, next I want to talk about this work, GRASP, which is work by Yusuf, Jair, and myself. So in Siesta, we basically use the very commonly used rehearsal policy of randomly select a certain number of examples and use them to update the network, where we're randomly selecting up to our budget. Here, what we ask the question, is there a more effective rehearsal policy in terms of what we should select for rehearsal than just sampling uniform from a class balance kind of distribution? And a lot of people have worked on this anecdotally. Like I've heard a lot of stories where they're like, yeah, we tried it, it doesn't work. We can't find anything that works. Anything that, people tried lots of methods and they all kind of work about the same or worse. Kind of depressing. But we found something finally. So we have a method called GRASP, and the idea is basically pick the easy stuff first and pick harder things and then harder still. So that's basically the idea. Go from easy to hard. In order to form your, during learning, you start with easy and then you progressively get hard, kind of like a curriculum. If this is compared to like random sampling. By doing that little procedure there, we end up with, this is compute measured in terms of neural network updates. And here we're using, instead of latent rehearsal, what we call it veridical rehearsal, it's just raw inputs. We get 9.2 million fewer updates are necessary to reach the same performance as the uniform class balance system using rehearsal. And then that translates to 1.6 times speed up on the GPU. These are all trained on one GPU, same GPU. And output, even if we do memory constrained experiments, the reviewers demand things like this. And you can see here that it still works better than all the policies under various memory constraints and under various compute constraints, where we kind of like control for the amount of compute we're allowing, just as we did in the Siesta work. You can see that it consistently outperforms others. And it's and it works both with this veridical and latent. So we tried it out with Siesta, and it still works well, a little bit worse than using veridical rehearsal. We also showed it works with DERP and GDOM, and works for continuous text classification, works on long-tail data sets, and works on vision transformers. It's hard to publish a paper if you don't use a vision transformer nowadays. You get reviewers saying, use a vision transformer. Okay, next one is overcoming the stability gap in continual learning, which is again with Yusuf here. So the stability gap refers to a phenomenon that when updating on new data, performance on previously learned data degrades before recovering. So in continual learning, often we measure performance at the end of kind of like receiving all of our data for a new task, or a new batch, whatever you want to call it. And if you look at this, if you measure more at a more granular level, which was discovered or shown by DeLong et al. In this nice clear paper, performance immediately plummets and then slowly recovers by using a mitigation method. So we introduced a method that basically tries to overcome this issue and results in a 16x speed up here. We test two hypotheses for the stability gap, which I don't have time to talk about the methods here, but basically one hypothesis, excessive network plasticity. And the other one is that large losses due to the domain shift cause the problem. So, at the output layer. And we developed multiple methods to test these hypotheses. And we found that both are supported. The excessive network plasticity more so than the other, but both are supported by our experiments. And that leads us to develop this new method, which is we call it stability gap mitigation. It's not the most original name. Which alters how the optimization trains. So it's not like rehearsal. It's not like a non-rehearsal method. It's just a modified training method. You can use it with most continual learning methods. So like here's what we get. So here's versus rehearsal. Here's the offline model. So here's with just vanilla rehearsal. And you can kind of see, with a uniform sampling for the rehearsal, it's not working very well. Here again, staying still with uniform sampling, we're working actually better than the offline model. And this is learning ImageNet 1K and then places long-tailed, so 1,365 total classes. And it's 16 times faster. Works well across different buffer sizes and works to increase DERP and GDOM by 11%, 14%. And it's improved our mind's performance a lot across all buffer sizes. And it worked on learning without forgetting, which is a non-rehearsal method. In fact, if you just use it for classic remote learning, it basically fails utterly. But ours, it now is at 40% versus 5%. But rehearsal works a bit better. Anyways, thank you so much. I have to thank all my lab and my sponsor, especially Yusuf here, gave him a gold star for this work, because these are all his papers, right? With a lot of help from Jair and Tyler and Ron also helped with most of this work, although others were involved with some of the stuff in the background. So thank you. Continual learning has a lot of applications. I think we should design our algorithms for them. We should be thinking about scaling and efficiency. And I personally want my work to have impact. I don't want to just write papers for all of you. I'm sorry. I want to have real world impact. So the papers I presented are all available on arXiv. I have had a terrible time trying to get them published because the continual learning people, I don't get the continual learning people who are like, well, why don't you test on C for 10? Why don't you do this? I don't feel like the stability gap should be measured on these large scale problems or with this kind of where the network's already been trained a little bit, even though you show that it happens. So I'm kind of frustrated, but I think I want to do work that matters. So thank you so much.
Thank you, Chris. I see a raised hand, which I'm not sure we will have time to cover. Sorry, Antonio, we are in a bit of a rush, but thanks, Chris. And I'm not covering the possible question because Antonio can join us at the panel discussion later on, and I guess Chris will be there. Can you confirm this, Chris? Wow, that's news. So here is like a preview of what Chris maybe talk about in the panel discussion, if you ask questions along this line. And I guess, I don't know if this is another nail in the coffin of the class incremental stream, but you can discuss it later on in the panel discussion. It may be. Thanks, Chris. This was really, really an amazing